start talking about angular momentum. And to motivate the problem of angular momentum, we will start by considering the three-dimensional Schrodinger equation. In 3 dimensions, or 2 dimensions, you get the added complication of rotation. That's where the angular momentum is coming out. And then we'll look at the angular momentum as the generators of rotation and derive their expression in terms of operators. And then we'll look at the spectrum of the angular momentum operators. Basically, what kind of eigenvalues can they have? Okay. And then in the end, we'll talk about the explicit coordinate representation of both the operator and their eigenfunctions. Okay, so let's start with the three-dimensional Schrodinger equation. Okay, so we can write it in terms of the Laplacian operator and some three-dimensional potential. And I'm writing down the time-independent case. So this is the three-dimensional eigenvalue problem posed by the Schrodinger equation. Let me give you an example, the easiest one, which is a particle in a three-dimensional cube. Okay, so we have some cube, and length is L. So for this problem, and we consider that outside of the cube, the potential is infinite, inside is 0. So in every direction, in the x, y, and z direction, which I'm going to label as such, x, y, and z direction, you'll see a infinite square well. So you can, first of all, this problem is completely separable in Cartesian coordinates. We can just write down the eigenfunction by multiplying together the respective eigenfunctions in the x and y and z direction for the infinite square well. So it's going to be this form. So to specify a wave function, you need 3 numbers, nx, ny, and nz. And the reason for this is in 3 dimensions we have 3 degrees of freedom. So it takes 3 quantum numbers to specify the energy. This is true regardless of the coordinate system you choose. Well, obviously, the Cartesian coordinate is going to have limitations. And in some problems, we favor either cylindrical coordinates or spherical coordinates. So let's start by thinking about cylindrical coordinates. Some problems that you can solve in cylindrical coordinates or a polar coordinate in 2D is, for instance, maybe you have an infinite plane and there is a magnetic field in the z direction. And then you have an electron trapped in 2D and it's moving inside of this external magnetic field. Okay. The natural coordinate system to use is polar coordinate for this case. And polar coordinate is really no different from cylindrical coordinate. Okay, so then maybe we can talk about an ideal quantum wire. Maybe the z direction is defined this way, and then you have the rho direction, and the since rho and this is the phi direction. Okay. A quantum wire, or we can think about a very short quantum wire, which because it's very short, it looks like a pillbox. And now this is a quantum dot. And it's a quantum dot because of the confinement in all 3 dimensions. So let's work with this pillbox property. So again, we're going to make it very simple. We're going to say that the inside of the pillbox is held at a 0 potential, and then outside is infinite. So it's exactly the same problem as this, but the boundary has a different geometry. And this geometry favors cylindrical coordinate. The cylindrical coordinate we're going to use can be defined on this box, on this pillbox. So this would be the z direction, this would be the rho direction, and then into the page would be the into the blackboard will be the phi direction. Okay, and let's put some physical quantities here. Let's say that the radius is alpha, and the height is L. Right? So we write down the Schrodinger equation for this problem. And that just turns into writing down the Laplacian operator in the cylindrical coordinate. And that is given by this expression. We've neglected the potential term because we're thinking about things happening inside the box, and then later we're going to apply the infinite boundary conditions to quantize the system. All right. So now this problem, because the potential has no angular dependence, is completely separable in the cylindrical coordinates. We can start the separation of variables.
You may take the moment to define the partial subscript notation because it's not commonly used.
Oh, all right. So save some notation. I'm writing things like partial rho with subscript notation of partial rho, and then the second partial derivative would be partial rho squared. What happens here? Okay.
What's the radius of the quantum knot?
It's alpha.
Alpha.
It's not 2. It's alpha.
So
Yeah.
the phi was defined differently from the typical cylindrical coordinate.
Why is that? We have rho and phi giving z. I know phi should be here, but
Well, phi is still like defined.
yes.
Yeah, usually people define the phi to be orthogonal to rho hat. Phi hat is orthogonal to rho hat.
Yeah, but the origin of these direction operators doesn't matter. So I've chosen them to all originate from the same position. But as you can see, if I take my hand into the rho direction and go towards the phi direction, then the z direction is this way. So it's the conventional definition. All right. So where were we? So we will start by trying to do separation of variables.
Those h bar square of the 2m.
Right, but okay, we can certainly. This is important. But now let me rescale the unit of energy. I'm going to measure energy in terms of h bar squared over 2m. So, but then we don't need this term. All right. So to do separation of variables, we just assume that this total wave function is given by a product of 3 component functions. And I'm going to use R to denote the wave function in the radial direction, and then the big phi to denote the phi direction, and then I'll use this Z, okay, to denote the Z direction. All right. So we just plug this expression into the above, and then each of these operators is going to operate only on one of them. So we can write that's the first term. Second term, and then the third term would be okay. No problems here. All right, so now let me pose 2 new eigenvalue problems to do the separation of variable. We're going to find the eigenvalue and the eigenfunctions of the d rho squared operator. And I'm going to denote this eigenvalue problem by And then another eigenvalue problem would be the eigenfunctions and the eigenvalues of the second derivative with respect to z. Since we haven't really quantized the system, we don't know what these things mean right now. But we can use whatever notation we like, and these are the conventional notations. We use n here because later we're going to quantize this, and you'll see it's something like an integer. So now if I go ahead and plug in these eigenfunctions into here, assuming that the phi and z are eigenfunctions of these two operators, then these expressions are replaced by these. Okay? And we no longer have partial derivatives in the phi or z direction. So we can write phi zeta, and then all of the phi and the z can be taken out of the expression. So this is like phi and z multiplying a operator that operates only on the r component, the radial component. And then this eigenvalue problem, the eigenvalue is replaced by minus n squared. Over here, the eigenvalue is replaced by minus kz squared. And now we separate the variables by canceling the phi and z from both sides. So we're left with 3 eigenvalue problems. Okay. 3 eigenvalue problems in the 3 different directions, components. Now let's deal with them one by one. Let me start with the z direction eigenvalue problem, which is the easiest. So for the z direction, we have and if you look at this potential in the z direction, it looks just like an infinite square well. So we know that in the z direction, the eigenfunctions are going to be square root 2 over L. It's going to be the sinusoid. And then the inside, we're going to have kz z. And because of this confinement in from 0 and L, we know that the kz's are quantized. And let me use since they're quantized, we can denote them, we can index them by a natural number. And let me use the number p in the z direction. So p pi over L. And we know that p belongs to the positive integers. So this is the z direction problem, which is just like a one-dimensional infinite square well. Then we turn to the phi direction problem. Obviously, the eigenfunctions are going to look like e to the plus minus I n phi. Okay. But if I look at the phi direction, there is actually no restriction. I can go a complete 2-pi rotation without encountering any barriers within the pillbox. So how do I quantize the phi direction? Now there are 2 ways. The first thing we can say is maybe under 2-pi rotation, the wave function should repeat itself. So if I have a wave function and I rotate it by 2-pi, then the wave function should be single value. If we consider that, so by using single value wave function, we conclude that phi of phi plus 2-pi is equal to phi of phi. And if I plug in an expression for it, it turns into e to the I and 2-pi is equal to 1. And that means the n's are.
Oh,
That means the n's are quantized to integers again. But these are just integers, not positive integers. But now there's a problem because when we say the wave function is single valued, actually in quantum mechanics, we only know the wave function mathematically. The wave function is not directly observable. What's directly observable is the magnitude square of the wave function. And that is the physical quantity that should remain unchanged under a 2-pi rotation. If we try to quantize it in that manner, then obviously, if I take a single eigenfunction and take its magnitude squared, I throw away all the information about n. But don't forget that we permit superposition of eigenfunctions. Okay, so the phi might be a superposition of two eigenfunctions with eigenvalues n1 and n2. So now if I compute the magnitude squared of this thing and apply the single valueness under 2-pi rotation, what I will get is, so this squared, let me write this out for you. So we're going to have two ones, okay, so 2 and plus 2 cross terms. Now under 2-pi rotation, we want this wave function, this magnitude square of the wave function to remain single valued. That means terms like e to the n1 minus n2 times 2-pi should be 1. So really, we can only quantize the system up to saying that the eigenvalues are separated by integers. Plus, let me use maybe an integer like q. Okay, and q belongs to the integer. All right. So now we will impose a symmetry condition saying that the eigen for this d phi squared operator, the eigenspectrum should be symmetric about 0. Because the d phi really is saying that if I imagine this e to the I n phi, okay, for positive n, I'm going in the clockwise, counterclockwise direction. Okay? If I look from the minus d direction, okay? I'm going in the counterclockwise direction. And then for minus n, I'm going in the clockwise direction. And we should say that the counterclockwise direction is no different from the clockwise direction. So any kind of rotation in these two directions should be the same. So that means the eigenvalue spectrum is symmetric about 0, meaning that either the eigenvalues are either half integers or integers. Is everyone okay with this argument? This is the more physical argument. So by requiring that a observable, which is the magnitude squared of the wave function, which is the probability distribution, to remain unchanged under a 2-pi rotation, we're able to quantize, also using symmetry of the clockwise and counterclockwise direction. We're able to quantize n to half integers or integers. And later we will use a different argument to arrive at this. And the half integer spectrum is very important in the case of spin. And for angular momentum, we can mostly stay with the integer spectrum. So these are the two eigenvalue problems in the phi and z direction. So now let's work with the rho direction, the radial direction. And let's assume that we're sticking with the integers in this case. And later we'll see what that means. Right, so let's assume n is an integer, and then let's work on this eigenvalue problem. So I'm going to work over here. So we would like to replace the E, since we're now measuring energy in terms of the unit h bar squared over 2m, and we know that energy is something like h bar squared k squared over 2m. So let me replace the E with k rho squared, representing the wave number in the no, not k rho squared. Let me just replace E with k naught squared. So this is the total wave number. So now we can manipulate this equation and turn it into a form like 1 over rho by putting this on this side. Sorry, there's to be a minus sign. By putting this on this side. Oh, wait a minute. We forgot a minus sign. Otherwise, this wouldn't work because I've eliminated the minus h bar squared over 2m from here. So there's a minus sign on the other side. So there's no problem with having a minus sign here. If I put the kz on this side, I get minus k naught squared minus kz squared r. And let me define this quantity to be k rho squared, which is the wave number in the radial direction. Now let's work with this side. Okay. We're all familiar with we're certainly all familiar with an operator that looks like this. So let's separate this into okay, so what is d rho rho? Okay. I can separate d rho rho by thinking about how they commute. Right? I can take d rho across rho by adding the 1. Because if I take the derivative with respect to rho, I get 1. So this is 1 plus rho d rho, right? So because these operators, I can think about 1 over rho d rho and d rho. I can think about all of them as operators. Now these operators don't commute, but their multiplication is associative. So I can choose to evaluate these two for a certain unit. Right? So I can just go ahead and replace this expression into there, yielding 1 over rho times something like this. And then this is, of course, separated into 1 over rho d rho plus d rho squared. Okay, everybody follow? So now the eigenvalue problem turns into d rho squared r plus 1 over rho d rho minus. Now let me turn this into the usual sign convention for the Schrodinger equation, and that is to negate the second spatial derivative. So in that case, so this is in the form of some kinetic energy plus a potential energy is equal to the total energy. So notice, what is this term? This is some kind of potential energy because it's only a function of rho squared. It's only a function of rho. We don't have rho derivatives in here. What kind of a potential energy is this? If I plot it out, first of all, it's scaled by n squared, and we said that n denotes the amount of rotation in the z direction, right? And then if I plot out 1 over rho squared, it's going to look, the potential is going to look something like this, right? So as I approach the origin, the potential blows up, meaning that the particle, if it were to experience this potential, would tend to get expelled. And the amount of expulsion is given by its amount of rotation in the z direction. Is this clear? So this is actually, in classical physics, we encounter this as well. This is called the centrifugal barrier. If I have rotation, that's equivalent to having a potential of this form. And this potential is going to tend to push particles in this direction. And actually, the gradient of this potential just gives you the centrifugal force. right? Now what about, so this term is, we're familiar with, second derivatives always represent some kind of kinetic energy. What about this term? Okay. So first of all, you might be worried. Okay. If I look at the appearances, so second derivative, we know that this should be Hermitian from our previous experience, right? This should be Hermitian, but now I have a function of rho times a derivative of rho, only in this order. Now this might not be Hermitian, okay, by the look of it. But now, is there a problem? Is our eigenvalue problem a eigenvalue problem of a Hermitian operator? It is. And why is this or this Hermitian or not Hermitian? What's the difference when I go from the one-dimensional problem? In one-dimensional problem, I have some potential d of x, and then the Schrodinger equation is written as minus dx squared phi plus d of x phi is equal to e phi. What's the difference here? Going from the Cartesian coordinate in 1D to the cylindrical coordinate in 2D or 3D. Not quite. In 1D we had x, the range of x was minus infinity to infinity, right? So we're operating on the whole real line. Okay? But for rho, what is the range of rho? It's from 0 to infinity, right? So neither of these are actually by itself Hermitian on 0 to infinity. But this operator that we started with, if you check this is certainly Hermitian. Okay, so there's no problem here. But you need to remember that you can't take a problem in cylindrical or spherical coordinates where you have a radial problem and think about the same way as you think about Hermitian operators on the entire real line. Because now you have the half real line. This is very important. Right, so no problems here. And now, and also we've given a physical meaning to this term, which is called the centrifugal barrier. This models how much the wave function rotates in the z direction and hence how much is expelled away from the origin. Right? So now, instead of solving that equation, I'm just going to tell you that this is the nth order Bessel's equation. Okay. That's the nth order Bessel's equation, and Bessel's equation you can write the two, because it's a second order differential equation, there are two independent solutions. Right? And the solutions are determined by the quantum number n. Now this makes sense because how much it rotates is going to determine its total kinetic energy. So it's natural that the radial component is determined by n, and we write the two independent two solutions as this. This is called the Bessel's a function of the nth order, and also we have the yn of 0, the Neumann function of nth order. So this is Bessel, this is Neumann. Unfortunately, there are no closed form solutions for them because we're essentially the cylindrical coordinate is essentially a 2D problem if you forget about the z direction. And in 2D problems, you often don't get closed form solutions. But we can talk about the asymptotic behavior. For the first of all, the behavior at the origin. The Bessel functions, they are regular at the origin. Right? But the Neumann functions are singular. So remember we always want to impose that our wave functions are normalizable. That is always a physical constraint. So if my solution domain includes the origin, then I can automatically throw away the Neumann functions, which is, in this case, I can do that. Right? Because certainly we include the z-axis. So and then close to the origin for small argument behavior, I can say that the Bessel function of nth order and for n an integer, this is approximately given by to the nth power. Okay. And then over here, this singular behavior is actually modeled by 2 over 3 to the nth power. And this is for small argument. All right. What about large argument? Large argument we can actually directly read off from this differential equation here. If I'm far away, if I'm far enough out into the rho direction, then I can say that 1 over rho squared is almost 0. Forget about the 1 over rho term because it's also very small. Then you just have minus the rho squared is equal to, which is again a free particle problem. And we know that the free particle problems either we have traveling waves in both directions, or we can cast them into cosinusoids and sinusoids. Right? So the large argument behavior are sinusoidal or cosinusoidal, and let me tell you, without giving you a proof, that this is the cosine and this is the sine. Okay, and this has to do with their singularity at the origin. So these are the behavior of the Bessel equation and the Neumann equations, and we are not going to try to give you show you how to solve them, because if you solve them by a series expansion, they won't converge and they don't have good analytical expressions. But let me plot out for you what the first few Bessel functions look like. Well, let me do the first 3. Since we know the small value or the small argument asymptotic behavior, okay, for the zeros order, it's going to be 1. So our equation, Bessel's equation, is going to start from 1. This is Bessel's equation, and this is the rho direction. Okay. And then far away is going to be cosinusoidal. Okay. So without showing you why, I'm just going to draw it out. That's the first one. For the second one, that's the zeros order Bessel's equation. So let me label this with zeros order. So now the first order equation, the curves come out as a linear function. And there's actually a relationship about the derivatives of the adjacent order Bessel equations. And we're certain that when a higher order Bessel equation crosses 0, we find a minimum or maximum for the previous Bessel function. Okay, so notice how I'm matching these and these 0 crossings with the maximum and minimum values, right? And then for the second, so I'm going to label this with the first order Bessel equation. And then for the second order, everything is the same. It comes out as a quadratic function. But now I run out of a line to label it, so let me just use this. Okay. And then to draw it further, you use the same thing, right? Whenever the first order equation reaches a maximum or a minimum, you will get a 0 crossing for the second order equation. Right. So that's it. That's all we're going to talk about for the Bessel functions and Neumann functions, and their behavior are very well documented. So now let's talk about how do we quantize the system in the rho direction. So since we said the Neumann function can be discarded because our solution domain includes the z-axis. So we're sure that the radial function is just some multiple of the nth order Bessel equation. So now I'm going to impose the condition of vanishing wave function at rho equals to alpha, because I have an infinite potential outside. This means that k rho alpha for the nth order Bessel equation must be 0. So k rho alpha must hit a root of the nth order Bessel equation. And you'll see that the Bessel equation, they have many roots because they're cosinusoidal already. Alright? So let me denote the mth root. Okay? The mth root of the nth order Bessel equation by this. How do you pronounce this?
This is C, right?
This is Kusi. What about this? The one with 3.
What is data?
That's
Data
so this is zeta, this is zeta, right? So let me denote it by zeta. Okay. So then I get k rho, the mth k rho is equal to the mth root of the nth Bessel equation scaled by alpha. So now the system is fully quantized. Right? And I can write down the energy eigenvalue as k naught squared is equal to, let me put in so I can write E is equal to h bar squared over 2m of k naught squared. K naught is just, so we have this Cnm over alpha squared plus the kz squared. Kz squared is just p pi over